All right, well, let's get started. Yeah, there's a lot to get through in this workshop. Um, yeah, so basically, in terms of where we're at with dynamics, last lesson we talked about work energy methods for particle kinetics, and we're kind of building on to that with today's lesson, which is on impulse and momentum, still for particles. Um, Yeah, and then looking ahead, there's also the lesson that we have on Wednesday as well as Friday. And I'm not gonna lie, for those ones, uh, there's a lot of content, right? Um, so I'm just yeah, I guess in terms of my own preparation, I'm trying to find a way to pack everything into those lessons. But anyway, I'll stress you out. But today's lesson, we'll just be wrapping up um, particle kinetics, and I don't know. I think something about this lesson is very interesting because you need to pull these kind of skills that you've learned from every other dynamics topic that we've talked about so far, and you'll see in the questions that that I have lined up. Yeah, you'll see that happening. So in terms of our lesson plan today, I'm going to be talking about impulse and momentum first, which is the new content. And then we'll go on to some worked examples, and then I'll talk about collisions, which is still new content. And then we'll have our quizzes just before the break for theory. And then, as usual, during the break, I'll put up the attendance and stuff. I've decided to do question 5 before 3 because 3 takes longer. And I think doing 5 first will help for understanding. I've also decided to leave question 4 out. I've included the solutions for it at the bottom of the notes, but yeah, that one's not particularly hard, so it should be fine. But at the end, I've allocated this little thing to talk about force time graphs. And this might actually take a while because I've actually got a worked example as well to go through as well. So anyway, there's a lot to get through. Yeah, I guess the difficulty of this topic is that questions can come in so many different forms, right? And yeah, so before we get started, I just want to clarify some notation which I'm going to be using in this workshop, because you'll see that even in maybe the solutions provided by the school, or I don't know, if you find your own questions. Actually, if you even look at my extra practice questions, some of them might not even have consistent notation. But for this workshop, I'm going to be presenting everything with this notation. So basically, when you see a letter, like A, B, C, whatever, that represents an object, right? So I'll just quickly draw an example out. If you see 2 boxes going together like that, that'll be box A and that'll be box B, for example. Yeah, and then 1, 2, and 3 represents different states, so at different points in time. Yeah, so you might see this is the initial state, right, of these boxes, and then say the boxes bounce back, right? It'll be like BA2, BB2. That's the notation I'm going to be rolling with, right? You might see heaps of different ones even in the lectures or whatever. It might be VA prime. They might not even call the objects AB. They might call it V1, like object 1, etc. So it's easy to get confused, but yeah, for this whole workshop, I'm going to try to keep the notation consistent. One other thing is sometimes I realize I label things randomly just numerically without thinking. Whenever I have something that looks like that, I've just kind of stored the equation, and then I'll come back to it for simultaneous equations or something like that. But yeah, that's just a quick tangent. I'm going to check the chat if we have any questions. And in person, do we have any questions? Okay. Cool. And so without further ado, I'll just get started. So yeah, impulse and momentum. This shouldn't be super new because you've probably heard of these words before from physics 1A, but that'll be the focus for today's lesson. In the lecture, they call J, or what I've called J here for impulse, call this I. but we're referring to the same thing, which is impulse, right? And basically the gist of it is that impulse is the change of momentum. And here for this formula, I've written it down as between states 1 and 2. That's like your change of momentum, right? But if you rearrange, I think it's something to do with F equals ma, that formula, right? You can find some sort of like derivation for this, but impulse is pretty handy as a formula because there's two versions of it. One is the force-time relationship, and one is the mass-velocity relationship, right? So that's just like the general formula for impulse. So yeah, usually what you'll do is you use this part of this formula, right? So that you can, anyway, you get the idea. In terms of conservation as well, so here we have a very similar, pretty familiar kind of equation. Where we have the initial momentum and then you add on some sort of change to the system, and that equals the final momentum, right? And here, I've just added in the momentum equation, right? And for the momentums, and then Ft, the force-time relationship for impulse, in this formula, for example. I won't talk too much more about that. So this is the gist of it, this is the basic idea, but here's where it gets interesting, right? So I've got two examples to talk about, which are pretty common in momentum and impulse. So pretend you have two states, right, for the first case. So we have two balls colliding either elastically or inelastically with each other, right? I'll explain those terms a bit more in a bit. So that's ball A, and that's ball B. They collide at some point. So I go in different ways. In which case you can use this formula in either of these cases, elastic or inelastic collisions, right? Where the A subscript denotes object A, the B subscript denotes object B. Just note that with the velocities, the masses don't change between states, right? So in the first state and the second state, the masses stay the same, but velocity will change, right? So that's why you have to have the letter and the number subscript for velocity, right? In the second case we have here, we have two cars colliding perfectly inelastically and gluing together, right? So there is a difference between perfectly inelastically and elastically. And I'll explain a bit more after I do question 1 on why that is, but I'll just give you the rough gist of it first. So again, pretend we have two states, right? Do my best to draw a car here. If this is car A and this is car B, right? Basically, say car A is going a lot faster than car B, or maybe car B is not moving at all, or whatever. And say they weigh roughly the same amount, then when they glue together, they're going to start heading to the right, and the masses will become intertwined. Mass A plus mass B. So that's a perfectly inelastic collision, right? And so that's just kind of what I represented in this bottom equation. Another thing to note is that for this bottom equation, it's kind of redundant information to say like this, like the velocity of car A and B together, state 2. So, and also it's just confusing. So I've just left it as v2, which is the cars moving together at speed in the second state, right? Okay, do we have any questions regarding that for the moment? Check on. Yep, I think everyone's happy. Very good. Okay, so here for this first question, I've redrawn that first question with some weird looking cars. Basically what's happening is this car on the left is being towed by the truck or pickup truck or something like that on the right, and yeah, and basically what V1 and V2 denote is these objects are moving together, right? And V1 is the initial speed, and then it linearly increases to V2. That's what the question was stating. And it tells you the time interval, which was 15 seconds as well between this happening. And it also states in the question that there's a rolling resistance of 500 newtons. So firstly, what is rolling resistance? We've never seen this word before, but it's effectively the same as your kinetic friction force, right? That's just what rolling resistance is. So yeah, when we draw out our free body diagram, you'll see that this is just a consistent vector acting to the left, right? It's going to be 500 newtons, so that's your rolling resistance, right? Okay, so I'm going to draw the free body diagram of the car, right? I'm going to be lazy, I'm just going to draw it as a particle. So when I say the car, I'm talking about this car here. The normal force going up, we have the weight force going down, the rolling resistance, right? And we have the tension in the rope. I'm doing blue. We have the tension in the rope acting kind of diagonally, and it's acting at 60 degrees from the horizontal. We know that because of our Z angles, right? Oops. Cool. Yeah, so all I'm going to do is I'm just going to analyze the horizontal forces. Because unlike normal, we don't need to go from weight to normal to friction because we're already given friction, right? For the rolling resistance, so we don't need to do the vertical forces first. We just know that this is 500. And okay, so in the impulse formula, right? So remember the impulse formula for the force-time relationship looks something like this, right? This F in the formula represents the driving force. I've never used that word before, but essentially it's the sum of the horizontal forces pretty much, right? So it's the thing that causes acceleration. So let me just write out the momentum, conservation of momentum. So pretty much this F here is your sum of horizontal forces. And that's not a blanket rule, so it's only the sum of the horizontal forces because of our setup here. It's not accelerating up or down, right? So what I mean by sum of the horizontal forces is this F is just the driving force that's causing the acceleration, right? Anyway, so I'm just going to plug in all my numbers. We know that the mass was 1,200. We were given our velocity, which was in kilometers per hour, but I've converted it to meters per second, right? So here for F, I'm subbing in our sum of the horizontal forces, right? So there's a few, yeah. So F equals that, right? And that goes into here, right? And then our time was over 15 seconds. Our mass stays the same, and that equals V2, which was this after we converted it from kilometers per hour to meters per second. Once we rearrange for T, which is the only unknown now, we get that T is this. So that's just a nice showcase of what this kind of like new tool in our arsenal that we have now, like what the impulse momentum formula can do, right? Being able to pivot from your force to, or having an extra tool to pivot from force to velocity and so on, right? Okay, good. All right. Do we have any questions in person? Okay, cool. So I'm going to talk about collisions now, right? So the first thing to note is our coefficient of restitution, right? Which is this, E. This isn't it's not that E. It's not the maths E, right? Not Euler's number. And so basically what our coefficient of restitution means is how much of, it's kind of like this, right? How much of our final velocity is conserved, how much of our initial velocity is conserved after impact, right? So if we're given 0.85, for example, 85% of the velocity from the initial impact is going to stay in the final impact, pretty much, right? So that's when you rearrange this to over here. So the final velocity is equal to 85% of the initial velocity. Right, that's kind of what we're talking about. And you'll note as well that here I've highlighted in red and orange the fact that B and A are swapped from numerator to denominator. And the reason for that is because of the nature of our impacts. And I don't know. So basically, like, they're bouncing towards each other, right? But the velocities have to go away from each other after the impact, right? Right, they collide and then the normal forces cause them to go the other way, right? So that's why those are flipped around, because the velocities are in the other direction, pretty much, right? Yeah, and then, so here's what I was mentioning earlier, but I'll go into it with a bit more detail. So E can be between 0 and 1. And when we're talking about an elastic collision, that's when E is 0. Do I have these numbers the wrong way around? Hold on. I think I have these numbers the wrong way around. Yes, okay, so an elastic collision is when E is 1, right? And inelastic collision is when E is between 0 and 1, but not including, right? And a perfectly inelastic collision So when E is 0. So that's what the case is when you have two cars that crash together and then they glue together. They don't separate, right? So that's a perfectly inelastic collision. And another way of saying inelastic, by the way, is plastic. I shouldn't cross it out. But yeah, plastic is just another way of saying inelastic, right? Okay. Yeah. Do we have questions so far? You know. One. Okay, cool. And then, so with our coefficient of elasticity, in the lectures I call this oblique central impact, I believe. But essentially, you have to remember our coefficient of elasticity only applies for our normal component of velocity. Okay, so the reason why most of the time it doesn't matter is most of the time you're going to be getting these questions which have impacts that are in one dimension, right? So that would be the normal component. But if you have this kind of case, you have to split the velocity into the normal and tangential directions. Okay. And then for the normal component, you apply, they call it central impact formulas, but that's just the E thing, right? This is your coefficient of elasticity. And for the tangential component, nothing changes. Okay. Yeah. So that's how it would work. There is one question in the practice questions which are provided, which will test your understanding of this. You'll see it in the quizzes as well. It's a bit of a funny looking question. So yeah, anyway. Yeah. Any questions on that? Okay. Okay. So moving on to the second question. It's kind of funny because like when I erased all my working for this copy of my notes, this is literally all the information you need to do this question, right? So there's basically, with these kinds of questions, you have two formulas that you can use, and there's basically two unknowns, right? So what we're looking at right now is we're looking at the initial state. So this is all the information we're given before the impact, right? And our two unknowns is the velocity of object A and object B after the collision, right? So in other words, our unknowns are VA2 and VB2. So that's what we're going to be solving for. And when we have two unknowns, we need two equations. And the first bit of information we have is that E is 0.6. So now we just plug it into our formula. And we can sub in our initial values. And keep in mind for these questions, right? So this is a one-dimensional question. We're going to take the right direction as our positive vector direction for velocity, right? So that one's going in +7. This one's going -5, right? So that's going to end up as a negative, right? When we rearrange that, I'm going to put VB2 on the left-hand side and get an expression for VA2. that'll be our first equation for our simultaneous equations, right? Second bit of information we know is our conservation of momentum. Right, which looks like that for an elastic or inelastic collision, right? And so we're given our masses, right? 2 and 3. Oops. And we already knew the initial speed for A and B, right? Keep in mind this is still a negative for B. And yeah, what we don't know is VA2, VB2, and so we're going to plug in our our equation that we solved for. You know what? I'm just gonna write this. Right? And we want to group all the VAs on the same side, right? And we can do a sanity check. We have a negative number for VA2, which makes sense because after collision, object A should be going to the left, right? We plug that into simultaneous equation, which is this pretty much, right? So we change VA2. And that's our VA2 and VB2, right? Do we have questions in person? Okay. So I've actually gone faster than I thought, but I don't know. These questions take a while, so I think we can have we can do the quizzes and have an early break, and come back and finish it off. I think that's the best way to do it. Because if I start doing question 5, there's going to be so many questions. Yeah, so I'll do the quizzes next. Yeah, if everyone could just join that, please. Yeah, if we have time, I'll go through question 4 as well. But I don't know. The next 2 questions and then the explanation for force time graphs will take a while. I'll just give like another 10 seconds to join. Oops, sorry. Actually, I think that number's not really moving. Alright, we'll just get started. Wait a minute. Oh man. Wait, I think the first question you can't get wrong. Uh-oh. Alright, we'll give like an extra 5 seconds for everyone to finish this. 10 seconds, man. I don't know. Most people to finish this. Alright, 3, 2, 1. Wait, 17% class accuracy. What? Okay. Congrats, Snowbill. Good job. Oh no. Wait, what happened? Okay, let's see. So it's a bit more evened out now, isn't it? Yeah. We're approaching that time in the term. So only go up from here. It's alright. It's good character development for everyone. Okay, so yeah, okay. To be fair, I made these questions like just before class, and I didn't have time to like think about how to make them fairer. So this is kind of like a wording thing, right? So it's a perfectly plastic collision. So elastic collision and a perfectly elastic collision are the same thing, right? And I can see why this is technically correct. Yeah, basically what I was looking for is that it's a perfectly inelastic collision, right? And then you can use plastic in place of inelastic, right? So the answer I was actually looking for was perfectly inelastic collision. Sorry, it's a bit of a trick question, to be honest. Okay, so this one is admittedly pretty, okay, they're all pretty difficult. Okay, so pretty much what I was trying to get at is that the normal component, so here's your surface, right? And then that aligns with the tangential component, right, of velocity. And that's your normal component. So what it's trying to tell you is that 85% of that will remain in terms of velocity after the impact. So that's where this question gets really cooked, right? I put this as like a 3-star difficulty question or whatever in the practice problems, and using the information that we're gonna talk about later in this workshop for questions 5 and 3, you should hopefully be able to solve this. Although, yeah, it's still a very hard question, to be honest. Yeah, this one's wrong because I said the net velocity is 85%, which isn't true because the tangential one is going to keep 100% of its velocity, right? And then that one's just, oh, that one's the other way around, yeah. And then just after dropping, it's a wording. It's basically just after dropping, as in like it starts at v equals 0, right? When you drop the ball. Yeah, it's about the collision, not the, yeah, I know. Okay. So so basically I will talk about that. Okay. Yeah, I'll talk about that one after we do question 3. And that one is not quite the same thing based on the formula. And then actually I'll talk about this one very soon. What do you have served? Oh yeah. Okay, so both of these are kind of hard because they're in the bit I want to talk about at the end, right? And then this one was what we're talking about in question 1. Okay. Oh, wait. Yeah, before I send you off on break, right? Let's talk about this quickly. Basically, for this formula, right? This is the integral version. So I've included the simplified version because for me it helps me to understand it at a glance. But that's the integral version, right? And it's also equivalent to the area under your force time graph, right? And we're talking about impulse here. So momentum, yeah, this is not the same thing for a for a force time graph. Yeah. Okay. I'll send you off in a break. Here's the attendance. Selection of 0 if you didn't get all of them. Oh yeah, that's true. So why does the tangential velocity not change again? Basically for a collision and the definition of E, which is the coefficient of restitution, you're only talking about the normal component. Yeah. I'll explain it properly after the break, but yeah, here's the attendance, so just scan that. Back in like 5 minutes or so. Also with this course, apparently the My Experience survey is out now on Moodle, and that's basically an anonymous survey which you can fill out, giving feedback on the course. You can give feedback to me. You can give feedback to the lecturer or the labs or whatever you want about the course, and yeah, it helps us improve the course. So please fill that out if you have the time. Yeah, if you enjoyed the course, if you didn't enjoy the course. Typically, those are the 2 types of reviews you get, the either end ones, right? So yeah, hopefully you did enjoy the course. That's what I'm trying to say. Is anyone in person filling out my experience by any chance? If you are, I'll give you some more time to fill that out before I continue the break. Yeah, but otherwise, we'll probably get started again soon. Oh boy, I didn't even know that. Okay, well, it gives me 1 day less to prepare, so hopefully it won't be too rushed for me. For reference, in my opinion, the hardest topic in this course is actually on Wednesday, not on Thursday. It's the rigid body kinematics. Rigid body kinetics is fairly similar to our work energy methods, impulse momentum methods that we've been learning this lesson and last lesson. You only have to modify it slightly, but rigid body kinematics is very different. But yeah, we'll get into it when we get into it on Wednesday. Okay. So yeah, basically just continuing. The question we got before the break was, why does the tangential velocity not change? So I don't really know if I have the perfect explanation for this, to be honest. But let me go back down to my diagram. So if you imagine like two pool balls or like two billiard balls or whatever, colliding at an angle, very similar to what you're seeing on this diagram right here, you can imagine that the tangential velocities of them aren't affected by whatever kind of inelastic collision component, right? It's just the normal ones will rebound a certain amount of the normal force or whatever. But the tangential ones, assuming there's no friction, should stay the same afterwards, after the collision. That's the best I've got in terms of an explanation. Maybe that makes sense. Okay. Let's continue. Right. Okay, let's digest this question, right? Because there's actually a lot to interpret. So it says that a 650 kilogram pile driver, call it object A, right? It's MA, right? Falls from a height of 1.2 meters. That's 1.2 meters above the pile, right? And it hits this numbers are wrong on the diagram. It hits object B, which is a pile that weighs 140 kilograms, driving it 110 mil into the ground, right? And the collision is perfectly plastic, right? So that's the same case as two trains colliding with each other and gluing together, right? Determine the average resistive force, right, from the ground to the pile. Right. Okay. So for these questions that are like more complicated, pretty much, you have to stop and kind of think about what is happening, right? So I'm gonna have to label a bunch of different states, pretty much, because we're gonna have to analyze a few, right? So I'm going to call it between state 0 and 1, you have the pile driver, object A, dropping, right? And why this is significant is because the previous questions we've looked at, like for example, two billiard balls, right? We're looking at it top down, right? It's something where we don't have to really consider acceleration, right? But now we're looking at an object which starts from rest, and then due to gravity, it's going to fall and hit another object, right? So there's going to be this acceleration going downwards. So the information that we're going to need to know is this, right? And then between states 1 and 2, that's when our collision is going to happen. Right? Yeah, there's not much more to say about that. We're going to need the additional information of the second object, like the mass of the second object, as well as the fact that the collision is perfectly plastic for that, right? And now there's actually another state to consider. And that's when the objects are merged together and then they displace into the ground, right? Okay, so wait, I'll also note down that in purple is the information we're going to need, right? And the end goal is to determine the average resisting force the ground applies to the pile, right? Okay, so for these kind of questions, I want to say generally there's two ways to solve it. So in question 5, I'm going to show you the first way, and then the next question, question 3, I'm going to show you the other way. So this one we're going to solve with work energy methods, right? From last workshop. Right. So here's what we're going to do. I'm going to split up my steps into the states that I was talking about, right? And we're just looking at pile driver A, the object A. Because object B is not moving and it hasn't been displaced yet because, yeah, so the energy in our system is just purely, like, we're just going to be focusing on object A here, right? Does this look familiar? Okay, so the first thing we can scratch out is that we don't have elastic energy involved because there's no springs, whatever, right? Okay. Next, in the system, I want you to think about if there's any work being done to the system. Okay, are there any external forces acting on A, right? And the answer is no, basically. There's no work being done. Everything's going to be driven by gravitational potential energy and kinetic energy only, right? All right, so now I've written down the Holy Grail equation, which we talked about last workshop, and obviously I haven't written the part to do with springs. So we know that the mass of A was 650, right? That's actually A as well. We know gravity is 9.81. So H is 1.2 meters, right? Because we're told that's how much it drops. And it's going to be negative because we have a negative change in height, right? Okay, and then it starts from rest. So from state 0, it's going to be at 0 meters per second. So now we just have one unknown, which is VA1. And then we solve for VA1. Get this, right? Yeah, so that was our first step. Does anyone have any questions so far? Check that one. Yep. Okay, cool. So we're just getting started pretty much. Because, yeah, as I said, I'm going to break up steps into the states, right? So for my next step, step 2, have between state 1 and 2. Okay, and so let's do a recap. So state 1 and 2, it's going to be a plastic collision. What formula are we going to use for a plastic collision? Right, that's the one where E is 0. So because E is 0, we're not going to be able to use that formula, right? Because we're not going to get any meaningful information out of it. All we have to do is use this formula. Right, so that's our conservation of momentum for a perfectly inelastic or perfectly plastic collision, right? MB was 140, but it starts at rest, right? So that term, well, since the initial velocity of B is going to be 0, that whole term is just gonna be 0, right? We found out in the last step that VA1 was 4.85, right? And now we just want to solve for V2, right? That's the only unknown. That's not too bad. What we do is we just rearrange. Just a second, right? That gives us V2, okay? I'm going to do something just to simplify the calcs in the next bit. And that's just to call MA plus MB big M. So that's just grouping them together. And that's 790, right? So in our next step, we're analyzing between states 2 and 3, okay? And here's where it gets a bit trickier, right? Because remember what happened is now they're combined, right? The masses are combined together. And yeah, we know the displacement into the ground is 110 mil. And we're still going to be using our work energy methods like in the first step, okay? You actually don't really need a free body diagram, but I'm going to do a free body diagram just to show you what's going on. Actually, is that even important? Yeah, sure. Yeah. Okay, sure. No, this is more confusing. Basically, we know the displacement is 0.11 meters, which is 110 mil, right? That's what we're given. Anyway, so we're just going to use our work energy equation between 2 and 3. We know that spring change in spring energy is 0, right? Okay, so think about work here. So is any work being done to the system? It's essentially like friction, but not friction, right? What's happening is that there's this resisting force that's going to cause work to, it's going to be causing energy to be taken out of the system, right? So work is going to be minus Fr, which is our resisting force, multiplied by that displacement before it stops moving. So that's kind of like the work done to the system. That's big M now, right, for our kinetic energy, because they're both moving together. Okay, big M was 790, right? G was 9.81. Okay, think about H, right? Between state 2, which is when it just collides, and state 3, which it's displaced, right? That change in height is just going to be the negative displacement. So between here and here, right? That's the change in height. And V3, right? So we know that the pile is driven and then stops moving, right? So that should be 0. Like it's driven into the ground and then at the very end it should stop moving. V2 is what we solved for in the second step. S, right? S goes that way for displacement, right? And this negative is what points the arrow the other way for that, right? Wait. That's not a good way to think of it, because we're thinking about it in terms of joules, which is scalar. So we're just removing energy from the system. Yeah, with that term here. Okay, so just going to simplify this a little. Okay, so what I want you to do, right, is think about this term in your head, right? Is this going to be a positive number or a negative number? Looking at the algebra and how that works. Because if you, yeah, just think about that for a sec, right? Okay, and so the reason is, right, what do we put here? 3.99 squared, right? That squared is not outside the bracket, right? It's inside the bracket. So what happens is you square the number and then you put the negative in front of it, right? So it'd be 3. It's like this pretty much, right? Oh wait, no, it'd be like this, sorry. Right, so anyway, that whole term is going to be negative. Right, we rearrange for FR. Get this. So that's the force that's resisting the motion, and it's going upwards, right? I think in the answers they do it like this. Kilonewtons. So it's just dividing it by 1,000, right? Yep. Does anyone have questions here? Yep, so Mohammed, I'll link you the timestamp in the previous workshop which I explained this, but just for the interest of time I'm not going to explain it again. It's in there somewhere. I'll find it and I'll send it to you, right? Okay. All right. So here's our next question, right? And this is a deceptively simple question. But yeah, what I'm going to do is I'm going to solve it with kinematics. It's kind of similar to our previous question just now. And what makes it tricky is the fact that we have friction, right, acting on it. I think the answers you'll find on Moodle for this question, they use the work energy method, right, instead. But I'll show you that, I'll show you the correlation between that method and kinematics, which you're allowed to use as well, right? Okay, so similar to before, we have state 0 to 1, right? So in state 0 to 1, basically, this block is stationary. The second, it's annoying because like they label everything differently to me. Yeah, I'm gonna call the block on the left block A, right, and the block on the right block B. Basically, block A slides to the right. That's the only thing that's really happening between state 0 and 1, but we have to consider friction, right? I'm going to highlight the relevant information which we'll need in the question for that. Right? Okay, and then between state 1 to 2, that's when the blocks A and B collide. Okay. And you're told that it's perfectly, you're told that mass B is 1 kilo and that it's a fully elastic impact, right? Which is another way of saying that E is 1. Yeah, and then lastly we have between state 2 and 3, which is that block B will be sliding this way, right? Actually, block A is also going to be bouncing back and going left, but the question doesn't really care about that. The question just focuses on what happens to block B after the impact. It says, how far will the second block travel over the same surface, right? Which has this friction. Yeah. Okay. And then before we start the question, you have to think about, does this coefficient of friction represent the static or the kinetic friction? Right. The only thing they care about is static, right? I mean, sorry, kinetic. Just lying to you guys. It's kinetic friction, right, that they care about. And that's because I guess just how the question's like set up. I don't know, actually. So it's just coefficient of friction. I guess in the context of the question, okay. I don't know if I'm over-explaining this. I think the graph will look something like this, actually. Let's forget this. Force applied. This is kind of how the friction gradient looks, right? So if they just provide one like that, that's what it's talking about. Yeah, I'll just keep that off to the side in case I need that again. But I think it looks something like that. Anyway, sorry, I kind of over-explained that. All right, let's get started pretty much. So between states 0 and 1. Right, let's draw a free body diagram for A. B is not moving, and we don't particularly care about the free body diagram in this step, right? Okay. So we set it up like normal, right? We always go like this, so we go from weight to normal. Because there's no other vertical forces, weight is equal to the normal force, right? And then we can substitute N here. And we can substitute this for the coefficient of friction that we were given. We get that this is equal to this, right? All right, so I'm going to take the sum of the force in the horizontal direction, right? We technically did the one in the vertical direction already, but we just kind of skipped that step. Okay, so we were given that the block A is 8 kilograms, right? And we've calculated Fk. And so this acceleration is purely it's gonna be negative pretty much, right? Because the only force acting on this system in the horizontal direction is going to be in the direction opposing the motion, right? So it has to be a negative acceleration. Right. And we were given that it travels a distance of 2 meters before hitting mass B, right? That's that distance here. All right, so I'm going to derive a function for velocity of A. So basically, that's that. VAO is 10, right? So that's going to be 10. The acceleration is what we just calculated before. And that's going to be multiplied by time, right? So that's going to be a function. I'm going to store that to equation 1, right? Actually, what I'll do, I'll just rewrite that to be a bit cleaner. I'm going to store that to equation 1, pretty much, right? What we're going to do is we're going to integrate this rather, with respect to time, which we get an expression for the displacement. All right, when we integrate, right, we have a constant, integration constant. It's going to pop up. But given that we know that at time 0, displacement 0, right? So we can set this kind of, yeah. So if this is our point of reference, right? So this is kind of like a datum, but in the horizontal direction instead, right? That's where s equals 0. And then, here, whatever, s is 2. Yes. Basically, at time equals 0, s is 0. We can just say that, right? And if we were to solve that, it just looks like this, right? I don't want to rewrite that step there. Right? When you solve for C1, that gives you C1 is 0, right? So C1 0. So we don't have to worry about that integration constant essentially, right? What we do have to do. Wait, what's it? Okay. So what we can do with this expression though is that when we set s is 2, so that's when it's here, right? So when s is 2, we can solve for the time that it hits the box pretty much, right? Yeah. So what I'm going to do is I'm going to set up the quadratic equation. So I'm going to move 2 onto the other side, over there. In general, I like to keep the constant in front of the t squared positive. So what I'm going to do is I'm going to multiply everything by -1, and 0 multiplied by -1 is still 0. So that's this. Right? So now this is quadratic equation. When we plug that in, get that. Okay. T either equals 20.195 seconds, or 20 is 0.202 seconds, right? So if we look at this, right? It's moving 10 meters per second, right? And it only needs to move 2 meters, right? So it's clearly not going to be 20 seconds. So t is 0.202 seconds. So you might be wondering why we have two positive numbers, right? Like from this parabola. And here's the way that I was thinking about it. Pretty much this box, right? It moves like this, and then it keeps moving, but from what we have currently told this mathematical equation, we've told it that it keeps like it'll move back left pretty much at 20 seconds all the way to this point due to our acceleration being due to the kinetic friction force, right? So it did this, and then the kinetic friction is like, whoa, we'll go back to there. However, obviously this isn't how it works in real life. That's just silly. And the whole reason goes back to this diagram. Once the force applied is low enough, what happens is there's this linear decrease in the frictional resisting force, right? Until it just stops moving pretty much, right? Yeah. Okay, that was just a bit of extra information. But yeah. Anyway, so yeah, but we haven't told that to the mathematical equation, which is why that still does that. Okay. Next, we're going to chuck in equation 1 again. Equation 1 was here. So we're going to be solving for VA1 specifically. And all we're doing is we're plugging in the time that we solve for, right? What this means is this is the velocity of object 1 after it just hits, just before it contacts the box, right? Like object B, right? Yeah. And our number kind of makes sense because it started with 10 meters per second. Now it's gone down a little bit to 9.802 due to friction, right? So that seems pretty reasonable to me. Check for questions. Answers are not on Moodle. Those answers will come up after the class. Yeah. All right. Do we have questions in person? Okay. Okay. So now we're going to work on step 2. So that was all step 1, by the way, guys. This will be between state 1 and 2. In other words, the collision, right? And the collision is fully elastic, right? In other words, E is 1, which equals, yeah, whatever. But the equation we're interested in using then is this one. Right? We know the masses of A and B. So just keep in mind with this question, because the numbers did look a little bit off to me when I was solving it. Object B is 8 times heavier than object A, right? So just keep that in mind. So we solve for the VA, A1. Oh, and then VB1, so it starts not moving, right? So it's actually 0. So that whole term cancels out, right? Yeah, and then so we're given this. We're just simplifying here. Yeah, and basically we're gonna end up with these two unknowns. Yeah, sorry, I did something slightly misleading a second ago, and that's that I was saying that E is 1, which equals what, all that stuff, right? Which is true, but we're actually gonna need to use that coefficient of restitution formula because we're gonna end up with these two unknowns, and so we're gonna need to do simultaneous. Right, so let's call that equation 2. So we've used equation 1 before. So formula. Sorry, just gonna move this around a bit. Okay, so from these we know that VB was 0, VA was 1.802, right? So these are our two unknowns, and we can plug in equation 2 here, which is this, right? When we multiply the denominator onto the left-hand side, and then what I've done is I've swapped the sides. So that's the numerator. Right. We just group the terms together. So VO2s, and then constant on the other side, divide them out. We get that VA2 is 7.624. Okay. So VA2 is the velocity of box A after it collides, right, with box B. And you'll notice that box A is also going to be moving to the right because it's so heavy. It's like 8 times heavier than box B, right? So it's also going to be ending up moving to the right. Using equation 2, we find that VB2 is this. Right. So that's the velocity of box 2. The question didn't actually ask for VA2, so you could have done it the other way around where you made an expression in terms of VB2 and plugged it in that way, but yeah, I just did an extra step pretty much. Do we have questions at the moment? Okay. Cool. Okay, so what I've done is I've preemptively drawn the free body diagram for B between state 2 and 3. So this is after the collision has happened, right? And the reason I preemptively drew it is because it's very similar. The only difference is that the weight is 8 times lighter, right? Which makes the normal force lighter, which makes the kinetic friction force lighter, right? Or less, yeah. We're going to do the same thing where we analyze the horizontal forces, right? And we plug in our kinetic friction force, which we solve for, and our mass, right? and we get this for our acceleration, which I think is the same as from step 1. And that's just because it's proportional to the mass anyway, right? Okay. We're going to make a function again. It's a very similar process from step 1 and step 3 here, right? Okay, so VB2 is what we solved for in our last step, right? That's our initial acceleration, and we're just making a function which can give us a number once we plug in time, right? Whatever time element there is. Okay, this will be sort to equation 3, right? I'm going to do the same thing where I integrate this to get SB. So this is our expression for displacement, right, of object B. So I'm integrating this term, then I'm integrating this term, right? And then we get this integration constant again, right? I'm going to call it C2. All right. So let's have a think about this, right? So before, do you remember how I said that our kind of like horizontal datum, our point of reference, was s equals 0 over here, and s equals 2 over here, right? Well, we can set a new datum for block B, right? Because this block hasn't displaced yet, right? So at time equals 0, yeah, I mean, okay, so basically we can also set a reference point in time, right? And t equals 0 here means once the block has just been hit, right? So that's what our function's describing. If you do this again, you'll find that C2 is 0, right? So now we have this function for SB. Okay. We have this kind of additional piece of information which I'm going to scroll back up to the question for, and that's that how far will the second block travel over the same surface, right? So think about what state 3 is. State 3 is when it stops moving. So it's done doing all the sliding that's going to do, right? So in other words, the block stops moving, and so VB, it's basically when VB is 0, right, at state 3. Right? And so this, let's call that equation 4. What we're going to be looking at is equation 3. So when it stops moving, right, we have our function. And then this is simple to solve for t. We're not going to have this parabola. We're just going to have this straight line equation, right? Because it only stops moving once, right? That's kind of how the maths works for this. Okay, and then plug in equation 4, having known the time at which it stops moving. And for each of these t's, we're going to be plugging in the time at which it stopped moving. Right? So when we chuck that into the calculator, we get that total displacement was this, right? And keep in mind, right, as block B, so that's S to 0. It's moved all this way. Now S is that before it stops moving, pretty much, right? And we set that as time equals 0. Time is, what was it? 17.76. Right. Okay. Is there any questions? If that makes sense. I think everyone's okay. It's good. So we have some time left, so I'm going to explain another question that's relatively, it's going to take a while to explain, right? It's to do with forced time graphs. I mean, if we have time, we'll look at question 4, but most likely not. So you can find my notes online after the class once I've uploaded it, pretty much on Moodle or Google Drive. Usually, like, I just go home and then clean up the notes a little bit. Might take like an hour or two. And then yeah, then I should be up. Okay. So for forced time graphs, right? The best thing I can do to explain them is show you a question related to it. So this is one of our extra questions which I've provided. And I think this question, okay, it's like slightly hard. I think I rated it 2 out of 3 stars difficulty. But I think it's really good in showing what I mean by like the area under a forced time graph, right? So let's look at the question. So this is force P that's pulling this block to the right. The block is 10 kilos. It's initially at rest. La-di-da. Yeah, we're given our static and kinetic friction, right? And then, yeah, we want to find the velocity of the block once time is 4 seconds. So that's the end goal, right? So the graph that we're given here is the applied force versus time, right? But our impulse, right? Our impulse is the area under this graph. Okay, in this case. So it's not equal to the applied force, but rather the driving force, okay? So that's kind of what I was alluding to in question 1. And it's going to look different to the applied force because we have to take into account friction, okay? So, okay. Let's just do the question. First thing I'm going to do is I'm going to set up a free body diagram. I'm just going to draw over the original diagram that they gave us. Right? Let's take the sum of the forces in the y direction. Right? That gives us that N is equal to mg pretty much, but acting upwards. Once we've done that, sum of the horizontal forces. Oops. Okay. Here's what we're going to do, okay? Because we're given not only the static friction, but also the kinetic friction, we have to assume that this whole system is static first, right? In other words, yeah, we'll solve it as if it's not moving first, right? And so therefore, if we're in static equilibrium, all the arrows pointing to the right should equal the arrows pointing to the left. In other words, P minus FF, right? That. Sorry. P equal, not doing a very good job explaining this. Okay. Fs max, right? Remember, that's your static coefficient multiplied by n, which is this. Right? Basically, what we've been solving for is this is the force at which it overcomes static friction, right? That's P. P equals 58.86. So you have to pull that many newtons before it starts moving, pretty much, right? Sorry, it took me so long to get there. My explanation is a bit fried there, but yeah. So let me just write that out again. Yeah. Okay, let's look on this graph real quick, right? We can map where P is in relation to time, because the applied force linearly increases with time, right? So we start at 0 and then we slowly increase the force, right, that we're pulling it with. So here, pretty much there's some time which we can map this to, and we just use our slope graphing techniques. Rise over run, right? Y equals mx plus b, that sort of stuff. Yeah, 25t basically, right? So that's our straight line function. And since we know P and we want to plug it in to solve for T, it goes like this. Rearrange for T. That gives that, right? So at that time, that's when it starts moving. That's when the box starts moving, right? Okay, so now the box is moving. Okay. And so we can take some of the horizontal forces again, and yeah, so that's equal to ma, right? But yeah, we'll just do this. Okay. So on this diagram, right, P is in the positive direction, right? So we do P minus Fk. So Ff is what I denote as friction force, but since we're moving it now we're looking at Fk, right? And that MA part just means whatever driving force is going to the right as a result of, yeah, these other forces, right? Solve for FK. So FK, so once the box starts moving, FK is constant, right? Like kinetic friction force is just going to keep happening as long as the box is moving, right? Okay. I'm going to draw out the graph which I was talking about earlier. It's time in seconds. Here is our horizontal driving force. Okay. And we know 4 seconds. These are our critical points in our graph. 2.35, right? Okay. So P, right? P equals 100 is over here. P equals 58.86 is here. Okay. So I want to calculate how this translates over pretty much into our sum of the horizontal forces. Here's how it works. It's basically I plug it into this equation, right? Right. Okay. And how this looks on a graph is like this. But this one is 60.76. This one is 19.62, right? Now we're finally getting to what I was talking about. We want to find the area underneath this graph, right, in order to solve for our impulse. One way we can do it is using integration, but being a civil engineer, I like to avoid integration wherever possible. So actually, I'll leave that there if anyone wants to copy it down. So simply, we just have a trapezoid, right? And so we can find the area of a trapezoid with this formula. It's basically you want to take the average height and multiply it by the base, right? And the way you do that is average of two numbers. It's like that. Agree? Average of those two heights is like that. Multiplied by this base, right? So this is that. So that's simply an area of a trapezoid. Right. Finally, so we've basically just been implementing this kind of formula. Okay, that's a lazy way of writing it, right? It's not technically that. It kind of is. Right. But anyway, that is equal to this, right? So V2 minus V1 is stationary, okay? And so when we solve for this, we have this, whatever that multiplies to, dot dot dot, is equal to 10 V2, right? Divide both sides by 10. We get that V2 is 6.6137 meters per second. Okay. And that is the speed, the velocity of the block when t is 4 seconds. Okay. Yeah, we'll just have a quick glance at this, but I'm not going to solve it. This is question 4. Yeah, sometimes you'll have to. I mean, you can do this in unit vectors, but I guess in this particular problem, I decided to solve it without unit vectors. Yeah. It was originally asking for the original velocity of car B, pretty much. So it's just like a matter of working through the formulas and finding that, but in 2D. Yeah. Okay, do we have questions in person? You're free to go, by the way, everyone in person. Thank you for sending the attendance. Will we be covering angular momentum questions? I think so. Yeah, it should be in the last workshop on Thursday. But not particle, not for particles, right? It's for rigid bodies. Yeah. Okay, thanks everyone. See ya. Thank you.